Hello, everyone. Thank you for joining us and welcome to this webinar about the Eco-Reuse Pulse Flow RO, also known as PFRO technology for water reuse applications. My name is Lior Eshed and I'm a product development manager and a member of the R&D team at ID Technologies. In light of the coronavirus outbreak, webinars are probably our best way to share information as there are no conferences currently. So I hope that you are safe out there wherever you are. And we'll start with the webinar right now. So thank you. So what's on the agenda? We'll start with a quick introduction about who is IDE, what is water reuse. We'll show the PFRO concept versus the traditional RO systems. I'll share some results from the Pismo Beach demonstration unit. I'll show some analysis of CapEx and OpEx. And go quickly over the applicability of extra high recovery using PFRO, end up with a summary, and of course, we'll leave some time for questions. So a brief introduction about IDE, for those of you who are not familiar with us. IDE was established in 1965, more than 50 years ago. It's a technology leader in desalination and water treatment. Started with, of course, thermal technology, and as RO membrane technology started to get into the market, switched more to membrane-based technology. More than 400 installations worldwide, offices in Israel, US, China, India, and Chile, as well as their partners worldwide. IDE is focused on three main sectors: desalination, seawater and brackish, industrial water treatment, and wastewater reuse. It's worth mentioning that in the desalination sector, IDE built some of the biggest desalination plants in the world, including Sorek in Israel, Carlsbad in California, Jamnagar for Reliance in India, Tianjin in China, which is the biggest desalination plant. It's a thermal desalination plant in China, and many, many more. IDE has a long tradition of innovation and puts a lot of emphasis on advancing the technology, as you will also see in this webinar about the PFRO technology. Some of the key innovations that were developed in IDE, among others, are pressure center design for seawater RO, 16-inch vertical pressure vessels like installed in Sorek, direct osmosis cleaning, and chemical-free desalination, also known as ProGreen, and many more. So I'll go quickly over a short description of the need, since I'm sure most of you already know about it. So why reuse wastewater? So of course, there is a growing demand for potable water. Another important feature is the diversification of the potable water sources to increase water supply stability. As they say in Australia and Perth, water forever, whatever the weather. I like that saying. Since it's a low TDS water source, it enables low pressure RO operation, so it's a cost-effective process. You don't need to go to very high pressures. It's abundant. It's an abundant water source. It's a proven technology, long reference list, and therefore also not something very new. So you can feel quite confident when going to water reuse, and there are strict regulations. So the water is pretty much very, very safe. So here is the water reuse process. We're starting with a wastewater treatment plant. In this case, this is an activated sludge process with a secondary effluent. The effluent from the wastewater treatment plant flows to the advanced water treatment. This is basically the water reuse facility, typically including at least 3 stages, starting with microfiltration or ultrafiltration to remove suspended solids. Then goes to reverse osmosis, which does the actual desalination itself, removing ions as well as organic contaminants, dissolved organic contaminants. And finally, UV AOP, UV disinfection with advanced oxidation, that is aimed to take care of any organic contaminants, residual of pharmaceuticals, antibiotics, etc., by having this high energy AOP process. The brine is usually disposed either to ocean outfall or whatever other source there is there for the brine. And the permeate either goes, if it is indirect potable reuse, which is basically all the cases, goes to either injection wells or other natural body source. The water then gets mixed with natural water in the environment and ends up in the production wells where it is being treated and supplied to the community. So this is the advanced water treatment, the water reuse facility. And typically, chloramine is dosed to the UF and sometimes also to the RO to control biofouling. However, the usage of chloramine has some disadvantages. First of all, it creates disinfection byproducts. When hypochlorine is injected to the wastewater treatment plant's effluent to form chloramine, it also reacts with the organic matter in the water and forms certain organic contaminants such as NDMA, haloacetic acids, and 3-halomethane. All of these disinfection byproducts pose a health risks and are not desirable, even though mostly degraded in the UV-AOP process, but still better off without them. Chloramine dosage has to be managed well, because if it is overdosed or there is not enough ammonia in the water, it may form free chlorine, which may oxidize the membrane surface and damage it. So it adds complexity to the system. Another issue is that chloramine lowers the UVT value of the RO permeate and acts as a free radical scavenger, therefore reducing the efficiency of the UV-AOP process. And I will talk about it later on. And of course, it also costs money, so it adds to the operational expenses. One of the key disinfection byproducts is NDMA, as I just mentioned. NDMA is a dangerous organic contaminant and a suspected carcinogen. In California, it is limited to 10 nanogram per liter, as well as in other places. And our approach or solution to avoid having NDMA formation is to avoid chloramine dosage by controlling biofouling and using innovative preventive maintenance methods to keep the membrane surface clean. In other words, just avoid chloramine and keeping the membrane clean using alternative methods. The typical limitations to water reuse in general, especially if you want to go to higher recovery, is fouling. Normally occurs because there is not enough brine velocity. It is a low shear force that is applied on the membrane surface. Biofouling, always a concern in water reuse facilities. Normally it is caused by stable and consistent hydraulic and osmotic conditions. And last, scaling. And the best conditions to have scaling is to operate long time in super saturated conditions and in hydraulically stable conditions, which is pretty much what happens in standard RO facilities. The eco-reuse PFRO technology tackles these limitations by implementing a different approach. Instead of having continuous flow, PFRO operates in intermittent flow. And I will go deeper into details right now. So a classic standard, also termed fully advanced treatment or FAT, is the standard RO facility, which operates at constant flows. In this case, you see a 3-stage water reuse facility, typically in the ratio of 1 to 2 from stage to stage. And the reason to design in this approach is because you want to maintain a minimum brine flow to overcome, to have enough shear force in the last membranes. In PFRO, there is a different approach. In PFRO, there is alternating flows. Therefore, there is no longer need to maintain this ratio of 2 to 1. We can operate at a single stage. And what we do in order to maintain enough shear force is that we operate in alternating flow regime. Instead of having constant flows like you have in standard RO, in PFRO, there is a brine valve, which is what you see here. Let me show you. This is the brine valve that you see here. This brine valve basically dictates the system's status. You can either be in production mode or filtration mode, or you can be in flushing mode. So the way that it operates is this. Each bundle of pressure vessels, typically 6 pressure vessels, have a common brine valve that opens and closes, this valve. When the valve is closed, we are in production mode. It is dead end filtration, and 100% of the feed water leaves as permeates. This is what you see right now. So when the brine valve is closed, all the water that is being fed into the system leaves the system as permeate. As permeate water leaves the system, the salts accumulate on the feed side, so the feed TDS increases and the feed flow decreases proportionally. Now we change mode and go into flushing mode. The brine valve opened, and the water that is left inside the pressure vessels, at least in the last few membranes, leaves the pressure vessel via the brine pipe, and does so very fast. So there is a high shear force. So what happens to the concentration is that it drops down. Why? Because the high TDS water left the system, and new water is being fed now to the system in the new cycle. When the brine valve opens, the water in the last few membranes, which is the saltiest, leaves the system as brine. It leaves in high velocity, thus creating a high shear force. In the next cycle, fresh water enters the pressure vessels again, and the TDS lowers. So there is ever-changing hydraulic and osmotic conditions in the pressure vessels. So what you see here in the graph now is the concentration. You see that it fluctuates. And if you compare that to standard RO, you see that as opposed to standard RO, where there is constant concentration, in PFRO, it always oscillates. When you look at the brine flow, you see that once the brine valve is closed, of course, there is no brine flow. But when it opens, you have a very high peak there, and it reaches very high shear forces. How high? About three to four times or even more higher than a typical RO. So every now and then, there is a high shear force that removes particulated matter or biofouling from the membrane surface, and therefore keeps the membrane clean. Let's look at some real data graphs that shows how PFRO works. So on the blue, you see the feed pressure. And as the TDS increases, you see that the feed pressure goes up. Basically, we move on the pump's curve. So there is a higher pressure and less flow. And once we are opening the brine valve again, going to flushing mode, you see that that the feed pressure goes down. It doesn't go down to zero, of course. It goes down about 20 psi or so, 1.3 bar, whereas the brine pressure and permeate pressure goes down more significantly. When we go again into production mode, the brine valve closes, and again we're in a new cycle. All this cycle lasts about 20 to 30 seconds. So each cycle is very, very short, and this is good because it doesn't allow scaling enough time to form. And I will elaborate on that in a few slides. So here we look at the pressure. Now let's have a look at the flows. This is the feed flow, and of course, as TDS goes up, as I said earlier, we move on the pump's curve, so the flow becomes lower and lower. However, the interesting thing in this graph is to look at the permeate flow. This is the graph here. You see that even though the TDS grows during the cycle, the permeate flow doesn't reduce because the pressure that the high pressure pump produces overcomes the increase in TDS. So altogether, we end up with quite stable permeate flow. Okay, let's go a little bit to the theory of scaling and how it occurs. So in order for a crystal to form, a few things need to happen. First of all, you need to operate long enough in order for the crystal to form. When a crystal forms, it goes through stage of nucleation process. Usually it happens around some particle that is on the surface. And then after that happens, then there is the crystal growth phase. And this is usually the longest phase, of course, and it is driven by diffusion. So, and this time here is called the induction time. The induction time is the minimum time required for a crystal to form. Once we are past that induction time, the crystal starts to grow with its three-dimensional matrix. And if you don't allow the crystal to get into this, you don't allow enough time for the induction time to occur, you don't basically allow the crystal to form. And this is what PFRO tries to do, is it tries not to allow enough induction time for the crystal to form. The other important thing for crystal is to have stable conditions, both hydraulic and osmotic. So PFRO doesn't allow these conditions due to the intermittent flow and ever-changing concentrations. This is a mathematical model that represents the actual time required for the formation of calcium carbonate layer. So what you basically see here is you see atoms moving in the three-dimensional matrix, and you see that it takes time for them to find the right place in this matrix. And once that happens, you see that they become stabilized, and then we start to see crystal growth again by diffusion. Basically, right now we're around this area here, the nucleation, all the atoms find the right place, even here. And once they are stabilized, you will see that it starts to grow by diffusion. And this is the point where we don't want to be. Here you see all the atoms try to find the right place, minimal free energy. And there we go. You see that it is all stable now. So basically, if you don't allow this to happen, then you significantly reduce the chances of having scaling. So we talked about scaling. Now let's talk about biofouling. So for a bacteria to grow and proliferate, what it basically does, it gains energy by metabolizing biodegradable organic matter, like the residual organic matter that we have in the effluent. And the best thing for a bacteria to do is to sit on the membrane surface, open its mouth, and enjoy the flux of nutrients. This is the best thing for bacteria to grow and form a biofouling. However, bacteria needs to waste energy if it has to cope with ever-changing hydraulic and osmotic conditions. It needs to produce certain metabolites in order to overcome these conditions. And basically, we tire the bacteria by changing the hydraulic and osmotic conditions. It is exposed to high shear force, it is exposed to ever-changing osmotic pressures, and so on. So it's a hard life being a bacteria in a PFRO process, and that's what we want to do. There is not enough or not a lot of free energy left for the bacteria to multiply and reproduce. So to summarize the differences between the PFRO and the fully advanced or a classic RO treatment, if you may. So as for design, in fully advanced treatment design, if you want to reach an 85% recovery, normally you need 3 stages using interstage boosters in between. In PFRO, it is a single stage design. There is no interstage boosters, therefore it is a whole lot simpler. The mode of operation in the fully advanced treatment process is that we operate in fixed and continuous hydraulic and osmotic conditions, whereas in PFRO, there is all the time alternating conditions, both hydraulic and osmotic. For scaling, so in fully advanced treatment, there is basically infinite induction times. It allows crystal growth by diffusion. Nothing is there to stop them, only CIPs. Whereas in PFRO, we do short operating cycles to zero the induction time. Therefore, we reduce the scaling formation considerably. For biofouling, in fully advanced treatment, there is low shear force, stable conditions that allow bacterial proliferation, whereas in PFRO, there is a high shear force and also rapid changes in their environmental conditions, hydraulic conditions that reduce biofouling. If you look at the environmental aspects of it, the use of chloramine to manage or control biofouling creates disinfection byproducts, such as the NDMA and others. whereas in PFRO, we don't use chloramine, so there is no disinfection byproducts. So altogether, it's a safer water being produced. And last but not least, but also a very, very important parameter, at least for the CAPEX and OPEX of it, is the operating flux. Typically in fat, we operate at 18 to 19 LMH. If you want to translate that to GFD, it is about 11 GFD, whereas in PFRO, we can do up to 50% higher flux. So about 28 LMH, or if you want in GFD, 16.5. So significantly higher. Now let's go a little bit to the results from the actual demonstration facility that we operated at Pismo Beach. So Pismo Beach is part of the Central Coast Blue. It's a regional groundwater augmentation and recycled water project that aims to protect shared groundwater while providing a sustainable local water supply for the 5 cities communities of Arroyo Grande, Pismo Beach, Grover Beach, and Oceano. The idea behind this project was to increase the groundwater supplies for the area by more than 30%, reduce seawater intrusion, reduce ocean discharge, and increase the region's water supply resiliency. As part of this effort, a water reuse demonstration facility was built to serve as a public outreach facility and demonstrate new technologies, and ID was lucky enough to be part of this project. So here you see this is Pismo Beach is pretty much in between Los Angeles and San Francisco, a beautiful area. So the demonstration facility itself was built in order to compare the standard RO operation and PFRO. Started at the end of October 2018, and it operated in PFRO mode for about 11 months. And the main features of it was that it operated chloramine-free when it was in the PFRO mode. It was operated, of course, in single-stage operation versus two-stage operation when it was operated in fat mode. Operating recovery was 86%, 50% higher flux than standard during the PFRO operation, and no CAP was done throughout the whole time. This is very important. And as I will show later, there's considerable CAPEX and OPEX savings. I'll take this opportunity to thank our partners for this, WSC for managing this project, Carolo for collecting data and analysis, the city of Pismo Beach for hosting us and help on site, Paul for supplying the MF, and Ivogwa for supplying the UV AOP. Paul MF was operated at 33 GFD flux with and without the dosage of ferric chloride and chloramine. Chloramine, of course, was dosed when it was operated in fat mode and was not dosed when it was operated in PFRO mode. And DRO was using Dow's Eco Pro 400 membranes. In the picture here, you see the 8-inch pressure vessel here. This was the first stage, and when it was operated in fat mode, there were 2 pressure vessels of 4-inch each that were operated for the second stage. When it was operated in PFRO, those were not in use, and they were disconnected. And here you see the Ivogwa UV AOP system. It is an interesting system since it was chemical-free AOP. And here you see the TSS and BOD of the effluent water. So the feed water to our system was secondary effluent from the local wastewater treatment plant. It was activated sludge, including nitrification. TSS was about 5 ppm with some fluctuations up to 10 ppm, and BOD was normally between 2 to 5. So pretty normal effluent. Here you see the performance of the MF. So the blue graph shows the log removal value by the MF, and the red graph here show the results of the pressure decay test, which showed to be below the max value at all time, basically showing that, that the integrity of the EMF was okay throughout the whole time. In addition, the pathogen's concentration, as you see below, and its concentration was in the filtrate was good as expected. It removed everything perfectly. This graph shows the specific flux. I think this is probably the most important graph. It shows the specific flux, and you can see the specific flux on the orange, I'm sorry, and the blue graph here is the recovery. So you see that the recovery was around 85, 86% throughout the whole time. And you can see that the specific flux was quite stable throughout the entire time, about 0.12 GFD per PSI. Note the high operating flux. And the operating flux was about 16.5 GFD from this point onwards, or 28 LMH. One also important thing to notice is that at the end of this test, we wanted to see how the system could operate without antiscalant due to the special operation mode of the PFRO. And we saw that even though we stopped using antiscalant here, and there was no increase or in the DP, or there was no decrease in overall performance. So we basically saw here that the PFRO gave us quite considerable I would say, advantages over classic fully advanced treatment. You can see all of these results in this publication here that we published recently. If you compare this specific flux to the specific flux of other well-performing water reuse facilities, such as the Orange County one, you see that the specific flux in Pismo Beach was around 0.12, as you see here, whereas in Orange County, you see that it started around here and gradually decreased. Here is where they had to do a CIP. So altogether, you see that there is somewhere between 20–30% higher specific flux overall. And also you need to take into consideration that the operating flux in Orange County was normal. It was around 11 GFT, whereas in Pismo Beach, it was significantly higher. It was 16.5. If you look at normalized head loss, you see here that the rate of DP increase was around 1 PSI per month in production mode. And overall, the actual operating DP was around 8 to 11 PSI. Here we sent 2 membranes to autopsy, so the DP decreased. But altogether, quite low values. If you compare that again to Orange County, you see that in Orange County, the DP was somewhere between 40 to 55 PSA in the 3 stages together, whereas in Pismo Beach, again, around 10 or so. One of the things that I started to talk about was the UVT. UVT stands for UV transmittance, basically how transparent your permeate water is. And this is important because the UVT has a great influence on the energy that is required by the UV AOP in order to reach the half-log removal of 1,4-dioxane as required by Title 22. So when we operated our system, when in the fat mode, when we dosed chloramine, we saw that in order to reach this half-log of 1,4-dioxane, it was required to dose around 685 millijoule per square centimeter, whereas when it was operated in PFRO mode, when chloramine was not dosed, only 450 millijoule per square centimeter was used. So 35% energy savings here on the UV AOP. Moreover, in UV AOP systems, normally you need to dose chemicals such as hydrogen peroxide or chlorine. And of course, higher UVT, if you dose chloramine, basically you will need to have more chemicals dosed. So significant OPEX savings here. When we looked at the permeates quality, So we see here a whole lot of pathogens in the secondary effluent, and in the RO permeate, everything was pretty much removed. So again, as expected, the log removal value was as expected. When we looked at organic contaminants, so out of 30 contaminants of emerging concern that we tested in the secondary effluent, 25 could be found in the secondary effluent. Only one of them could be detected in the finished water, and that was sucralose. Sucralose is an artificial sugar that is used in Coke, etc. And sucralose was around 65,000 nanogram per liter in the feed, and only 28 nanogram per liter in the permeate. So 3 log removal in the RO. So even better than the 2 log removal that is usually granted according to Title 22. As I said earlier, we sent a couple of membranes to autopsy, the first and the last elements. And that was important because some people were concerned that due to the oscillating hydraulic conditions in the system, maybe there is some mechanical damage. So it was very important to see the actual results after 11 months of operation almost. So no mechanical damage was found, as indicated by the fiberglass casing, brine seal, permeate tubes, ATDs, etc. Both membranes kept their integrity. There was very little fouling or scaling presence, as indicated by the membrane's weight. It was almost like new membranes. Also, the foulant density was very minimal as well. Permeability loss was also, whatever permeability loss was there, it was fully recovered when CIP was done. And also when you actually look at the pictures of the spacer and the membrane itself, you see that is very clean. So the PFRO was found to be very effective in keeping the membranes clean. Pismo Beach was not only a demonstration site, it also was a public outreach facility, and people came over, students, decision makers, etc. And one of the things that was done there was to do water tasting. And of course, it showed here that 70% of the people preferred the purified water over tap water. So we're happy with that. Here you see some pictures from the ribbon cutting ceremony. Again, we believe that having the public engagement in this effort is very important, as well as to demonstrate the technology, and also helping to optimize engineering for the actual full-scale plant whenever that will be built. So when we look at the RO skid that will use this technology, we're talking about, in this case, this is just an example, but this is what IDE has to offer in that sense. A train in this case includes up to 72 pressure vessels. It is fit in containers. So you see here that a 72 pressure vessels train will be based with footprint of two container 40 feet size containers in two floors. Here you see the pressure vessels and pumps here on the side. Now, if we look at this model and we compare the OPEX, including all manpower and other costs, and we compare that to the fully advanced treatment, you see here, this is specific cost, okay? This is US dollars per cubic meter. And since the PFRO operates at higher flux, it means that we can produce more water from the same equipment, from the same manpower, etc. So altogether, there is considerable savings here. You see that the energy, if you operate at higher flux, in this case, it is a PFRO 72 pressure vessels operating at the 20H or 16.5 GFD. You see here that the energy expenses are higher than FAT because you operate at significantly higher flux. but there are savings on chemicals because there is no chloramine dosed and less CIPs, etc. But since the same manpower will operate the single train, you can just produce more water from the same OPEX investment that you have. So considerable savings here. Also, when you look at CAPEX and you compare that to the fully advanced treatment, you see that since you produce more water, in this case, if you operate at 28 LMH or 16.5 GFD, you can produce around 30% or more water from the same equipment, then you have considerable savings on the CAPEX side, about 20-25%, depending on the exact case. If you look at overall project's life in years, you see that, of course, as time passes, the importance of OPEX becomes more relevant than CAPEX. And this graph here, the orange graph here, shows a comparison between the fully advanced treatment and PFRO operating at 28 LMH, 16.5 GFD. And you see that if you look at 20 or 25 years of project's life, you see that you end up with savings of overall CAPEX and OPEX, or water cost, if you may, of about 25%. And in the next slides, I will show an exact case study in which we looked at trains from the San Diego Pure project, and we compared that to basically a what-if analysis. If this project was to use PFRO, what would be happening? So in order to produce the capacity of water required for San Diego Pure, they required around 40 MGD. They needed 8 trains of 175 pressure vessels each, including interstage boosters, etc. If it was to be done using similar trains with the same amount of pressure vessels in each train, only 5 trains would be required. And the reason is because we could use more elements, at least 7 elements per pressure vessel. Again, the reason is because we don't have to worry about the shear force anymore. The shear force basically is taken care when we open and close the brine valve. And since we operate at higher flux, only 5 trains could supply the same amount of water. So you see that in the fully advanced treatment, basically classic approach, 8 trains had to be used, whereas in PFRO only 5 similar trains could be used. So not only you save on CAPEX, also you save on footprint and all those other fixed costs. So if you look at the water cost, CAPEX and OPEX of San Diego Pure, you see that after 20 or 25 years, you would be saving about 20% of the water cost. Okay. Now, one of the most interesting things that we see that is happening at the moment is that clients are looking for ultra-high recovery. When I'm talking about ultra-high recovery, I'm talking about 90, 95%, sometimes even more. This is especially relevant when there are cases of water reuse facilities that are located far from the shore, or they don't have easy access to brine lines, etc., and the brine is an issue. And those facilities would like to get the highest recovery basically available. So for this case, what we offer is to operate the first stage using PFRO, operating at 85 to 90% recovery with or without antiscalant as required, and then take this brine and go through a unit that we term desaturator. This desaturator unit basically takes the brine water, inactivates the antiscalants, and basically allows sparingly soluble salts to precipitate, and those are later removed as sludge. Those could be calcium carbonate, silica, calcium phosphate, and other scaling causing salts according to the actual water chemistry there. Then the water that is left after this goes through a UF in order to remove TSS. and go to another stage of PFRO, again, when anti-scaling is being dosed. So all this allows to reach 95% recovery or even higher. Theoretically, you could also do this for more than 2 stages. You can even go to 3 stages and more. And not less important is that the brine you release after all this is chemically stable. So this is the brine that you release here doesn't have any tendency to scale down the road. We basically don't transfer the scaling issue down the road to the pipe or to other accepting body of the brine. So we are pretty much at the end of this webinar. So let's summarize what we've learned. So CAPEX. Since it is a single stage design and most importantly, higher flux design up to 50%, there is considerable CAPEX savings here. On the OPEX side, there is no chloramine dosage. There are savings on fixed costs, such as manpower, civil. Again, you produce more from the same equipment, from the same fixed operational costs that you have. Overall water price reduced by up to 25%. You can reach high or even very high recovery depending on the need. You get with a very high UVT, almost 100% UVT, because you don't use chloramine. So you get savings on the UV AOP, smaller UV AOP facility. Since it is a chloramine-free process, there is no disinfection byproducts, no NDMA, haloacetic acids, etc. So safer water. And it's an environmentally friendly process because you use less chemicals, etc. One thing to add before we go to the questions, more of a general note. I presented here about the usage of PFRO for water reuse applications, but this technology is a platform that is also offered for other applications, such as brackish water RO and industrial water treatment. So basically the same also applies there. So with that, I would like to thank everyone for joining. I wish you good health and please stay home. So please, if you have any questions, this is the right time. And of course, if you have any other questions that you want to ask privately later on, please feel free to do so. So there is time for questions now. Thank you. And by the way, questions can be asked via the chat or the raise hand app there. So please feel free to use it. So I see that there is a question here, but apparently I cannot see it. Oh, here. Would this technology have any application in land-based brackish water desalination? So definitely yes. This same technology can be used for BWRO. In fact, we already did some designs for it. Yes, the same benefits will also be relevant there. Of course, in brackish water, there is less issue normally of organics, but there is always the issue of scaling, and those places there can enjoy those benefits. Another question here: does the improved efficiency of PFRO allow for higher TDS inflow to desal oil field produced water? So basically, this is a standard RO operation when we talk about higher TDS. Again, if the issue here is scaling, then yes, PFRO will give you a benefit. Typically, if we go to higher TDS, what we can do, as I presented one slide earlier, if there is any issues of scaling there, we can do several stages of PFRO. In each stage, remove part of the spiraling soluble salts, so we can end up theoretically with the osmotic pressure limitation up to around 8% TDS. So yes, this can also be done for IWT and also for diesel oil. Okay, one question also here, let me see, from Jan. Do you fully flush the membrane during each actuation of the brine valve? No, so not the full, not the pressure vessel itself is not fully washed. Only part of it. So around 2 to 3 of the elements is being washed. So it's basically tacts. You can look at it as tacts. One quota of water is leaving the pressure vessel, and the same amount of water feeds it again. So yeah, not the whole thing. Another question here. I've been waiting. Okay, so yeah, gently, Aga Khan, thank you for the question. You are definitely more than welcome to ask me later. What I meant was to ask by email. Okay. Any more questions, guys and ladies? One question, will the presentation be available on the web? Yes, definitely it will be available on the web, and also there will be a recording of this webinar, so please feel free to see it again and share, and yeah, enjoy it again. And I see that maybe there are some questions here regarding my email, so I will go to the first slide quickly. There, let me. Here, so you can see my email here. For those of you who are interested in asking questions later on, please email me freely. We're all at home, so I have all the time in the world to answer you. Okay, one I think important question here. Was the PFRO approved by the DDW for potable reuse applications? So, and this is an important question. Thank you for this question. So basically, since what we're doing here is using normal RO equipment, we're not doing anything special here. Yes, there is all the approvals required for this. Also, this was one of the things that we wanted Corollo engineers to be part of this. Is that all the information is gathered and presented to the authorities. And yes, all of this information was presented to the authorities, so no problem here. Another question, do you have multiple brine valves on a single large scale? How many pressure vessels? Yes, so what we do is that for every 6 pressure vessels, there is a single brine valve that opens and closes. So let's say that you look at a 72 pressure vessels skid like I presented earlier. So we have 12 rows of 6 pressure vessels. Each 6 pressure vessel has 1 brine. One important thing to say about that is that not all the pressure vessels brine valves opens and closes at the same time. They do so gradually. So there isn't a big difference in pressures through the time. Only a minor change in the actual pressure that the overall system feels. Another question, can we apply it without pilot demonstration testing? Yes, so this is basically up to you, and of course can be decided on actual case. We have pilots if required. If not required, then we can also skip that. How is your system compatible with FORO system? Forward osmosis, reverse osmosis system, I assume you mean here. I'm not sure that I understand this question. Dr. Muhammad Reza, maybe if you can elaborate, I will be able to answer more. So another question related to the flashing time. Is the flash time based on a set time or a conductivity reading? No, it is set on time based. There is also some other inputs here that is gathered in. This is quite a smart system, so we collect even some more information. I will not tell all the secrets right now, but basically it is based on time. Yeah, so forward osmosis combined with RO can save 20 to 30% of total cost. Mr. Dr. Muhammad Reza says, well, actually, I'm not too familiar with forward osmosis combined with RO. I do know that forward osmosis has its benefits, but also I think it is quite sensitive in many cases to organics and scaling. So I cannot really answer that. Maybe we can continue this discussion privately later on. Okay, so I think that there are no more questions. So I would like to thank you once again. And oh, here there is another question. In graph, you indicate UF in midsection, but you show pole MF. Doesn't it matter UF or MF? Yeah. So no, for us actually, it doesn't really matter if we use UF or MF. In Pismo Beach, we operated using MF. But both technologies provide good enough feed water to the RO. And by the way, if you look at it from a log removal credit perspective, both UF and MF provide you the same log removal credit. So the same quality here for us. Even though, I mean, everyone knows that UF basically provides better or cleaner water than MF, but it is still clean enough for the RO. Okay, so thank you everyone for joining. I wish you good health and happy day or night wherever you are. Thank you. Bye-bye.